Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? Space, John F. Kennedy once said, is the new ocean. And for more than half a century now, humans have been exploring this ocean. In doing so, we are moving in a deadly environment, characterized by cold, heat, and cosmic radiation. But one of the biggest dangers in space was put there by human beings themselves. Space debris poses a threat to astronauts and satellites. Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. Something has hit this pane and damaged it. Not really a dangerous impact, except that this pane is a window on the ISS, the International Space Station, 400 kilometers above the Earth. A tiny piece of space junk hit the ISS at an estimated speed of 8 kilometers a second. Hundreds of thousands of these fragments are hurtling through the Earth's orbit, and every one of them could cause a disaster. Ever since spaceflight began, man has also left his refuse behind in space. Satellites, spacecraft, and the International Space Station are permanently at risk of being hit, damaged, or even destroyed by particles of scrap. Astronauts are also at risk from cosmic radiation. Our sun, too, can mean death for humans in space.
Traveling in space is dangerous, really dangerous, and I know what I'm talking about. There's space junk, for example, millions of particles of debris orbiting the Earth. In this respect, humans have really caused themselves a problem. But totally different dangers also lurk, like gigantic cosmic rays, hard radiation which destroys our DNA, or solar eruptions which trigger off solar flares. But we're not totally defenseless in the face of these dangers. Today, there are solutions we can turn to.
Space for humankind is limitless, uncharted territory, and every venture into space is a risk. March 12, 2009, an alarm has sounded on the space station. A fragment of debris is on a collision course. The likelihood of impact is less than 0.1%. Nevertheless, the astronauts seek refuge in the Soyuz capsule that has docked onto the ISS.
There are 3 emergencies which are actually highly critical and call for immediate reaction. When fire breaks out, when the atmosphere is contaminated, or when there's a drop in pressure because, for instance, a piece of debris is hit. In such cases, everyone must know exactly what to do and do it at once. There is no room for error.
There is permanent risk of space junk crossing the path of the ISS. The piece of debris in March 2009 was about 13 centimeters in size. It passed the space station at a distance of only 4.5 kilometers. An impact could have been fatal.
In order
to stay in orbit, the objects have to travel at a high speed, roughly 7.5 kilometers per second. That's very fast. It corresponds to 28,000 kilometers per hour. When objects collide at that speed, the impact velocity can be up to 28,000 kilometers per hour. At such speeds, even a small object the size of a bullet has an enormous effect. In fact, you can't even compare it with a gunshot. The energies which are released are more like those associated with an exploding hand grenade.
Microscopically small particles can cause immense damage without warning.
The speeds are so great that you can't see anything coming. If space junk in the form of a screw were right in your path, you could not evade it. A screw would be too small for you to spot, so there would be nothing you could do. Consequently, all the objects that are flying around are detected, and we really have to be on guard to ensure that the space station or satellite is not hit by one of these particles.
Larger objects are monitored constantly by radar. If there is a likelihood of a sizable piece of debris crossing the orbit of the ISS, the space station performs an evasive maneuver. But the ISS must itself protect its occupants from objects that have not yet been discovered. The station is reinforced by shields, especially in the direction of flight.
These shields can fend off objects up to roughly 1 centimeter in size. This applies to the manned air-ventilated modules, which are fitted with these shields. In other words, the ISS is safe from anything smaller, and anything bigger than 10 centimeters is of a size that can be identified from Earth. In such a case, the whole ISS would carry out an evasive maneuver.
The most dangerous objects, then, are those between 1 and 10 centimeters in size. In order to calibrate telescopes on Earth, test objects are released into orbit from the ISS. After a short while, these mini-satellites burn up in the atmosphere.
Space junk is not all the same. It depends on how big the particles are and where they are. All particles larger than about 1 centimeter can pose a potential threat to satellites. They shatter everything, and some can be as much as several meters in diameter. But all these particles are fairly evenly distributed, so at any point in space you will find various kinds. Where exactly are these particles? Well, they are all located mainly in a shell around the Earth, up to around 1,000 kilometers from it. This is where roughly 90% of all space debris is found. Why that? Simply because most of it involves weather and Earth observation satellites. They need to be very close to the Earth in order to observe weather patterns and details on the Earth's surface. And then there's another, totally different area, geostationary orbit, fairly far out at a height of 36,000 kilometers. Here, satellites are positioned like pearls on a string. That's because they have to orbit the Earth at the same speed, and there are only a few slots for that, hence the string of pearls. But there are also a large number of dead satellites up there. They're located a little further back. So in fact, we have 2 strings of pearls, one behind the other. The satellites that are still functioning are closer to Earth. Those that are already dead are further out. Everything in between that we see in the form of particles of space scrap are navigation satellites or military satellites, orbiting in intermediate, highly elliptical paths from the inside outwards.
The biggest objects are all known. Their paths are constantly monitored. A kind of life insurance for the crew of the ISS.
Intensive monitoring and measurement mean that orbit information regarding the ISS is extremely precise. Its path is compared with the paths of some 17,500 objects, which are monitored regularly and registered in an American catalog. The ISS could fly close to some of these orbits, which are then highlighted and constantly compared with the space station's orbit. Should such an object come close to the ISS and the risk of a collision be estimated at greater than 1 in 10,000, the space station would then perform an evasive maneuver.
For the crew, a routine maneuver.
Performing an evasive maneuver doesn't involve any massive acceleration. The engine is fired for a minute or 2, and basically then you've done all that is necessary.
Emergency situations are rehearsed time and again.
Everything goes as smooth as clockwork. You do exactly what you've been trained to do. Quite honestly, there would be no difference between a simulation and this happening in real life.
Should there be no time for evasive action, to be on the safe side, the crew would disembark into the lifeboats, 2 Soyuz capsules docked on the ISS.
The crew has to be protected just in case some particles actually hit the station. In such an event, the crew would then be in the Soyuz capsule. It would then be a case of sealing the hatch, undocking, and returning safely to Earth.
So far, though, this has never happened.
Let's assume the ISS has an aluminum wall 10 centimeters thick. If it were hit by an ordinary particle with a diameter of 1 centimeter, this is the damage that would be caused. This is the simulated damage from a pellet traveling at 7 kilometers per second, the typical orbit speed. You can see at once that the damage is massive. The cone is about 5 centimeters deep, but a 10-centimeter thick wall on the space station is out of the question. That would make it far too heavy, so a different solution was needed, and that's why the triple shield was developed. How does it work? You make 3 walls roughly 2, 3, or 4 millimeters thick. The task of the first wall is to shatter the incoming particle. This creates a pile of debris, which hits the second shield. This second wall is able to withstand this cloud of debris, so it's not penetrated. And the third, usually very thin wall withstands the inner pressure in the space station. And that's how it works. The whole space station is equipped with this triple shield.
This outer shell is checked constantly because it is the astronaut's most important form of protection against the impact of a small meteorite or a piece of space debris. 60 years ago, the space age began with Sputnik 1.
After the Sputnik flight, there was no scrap in space. By today's standards, the Sputnik 1 mission was actually perfect. The mission achieved its goals. After a short time, the satellite and also the upper stage of the rocket that took it into orbit returned to Earth. And that's precisely what we want.
From the 1960s onwards, however, spaceflight experienced a boom. The space race saw more and more rockets being launched. In April 1961, a Russian Vostok rocket carried the first man into space, Yuri Gagarin. This marked the start of the era of manned spaceflight, and with every launch, more junk is delivered into orbit. Decades later, more than 2,000 parts from Gagarin's rocket are still hurtling around the Earth. The American space agency NASA, of course, also has left its junk in space. Increasingly powerful rockets are also leaving larger objects in orbit. In the early days, nobody was concerned. It is the upper stages of rockets in particular that can cause problems. They are like time bombs.
The first space junk was created back in the early 60s. In 1961, the upper stage of a rocket fragmented. And that is still a problem today. A rocket stage is designed for a service life of 10 minutes. That is how quickly it reaches orbit height from the ground. And nobody ever gave a thought to what would happen with this rocket stage over the many years it would remain in space. Conditions in space are extreme. There are enormous temperature differences when you leave the shadow of the Earth, then exposed to the sun, and again enter the shadow of the Earth. This happens within minutes, several times a day. No material can withstand this in the long term. We have residual pressure in the tanks. We are bombarded by micrometeorites. We have atomic oxygen, ultraviolet radiation, everything that causes material fatigue. It's only a question of time before these objects disintegrate on their own accord. So a large proportion of the fragments come not from collisions, but from such explosions.
It is a problem that still hasn't been solved. Nearly every launch results in parts left behind in Earth orbit.
But what kind of junk actually gets into space, and how does it come back? Let's look at the launch of a rocket. It shoots upwards, and the first stage is jettisoned. It floats down to Earth on a parachute and is reused. So it isn't junk. The upper stage flies into space and returns on a parabolic trajectory. It burns up to a certain extent, and the metal is resold. So that's not really junk either. Then there's the uppermost part, the fairing, the mantle which surrounds the satellite to keep it well protected. That stays in space. After a few months, it returns, a metal shroud that burns up completely in the atmosphere. That's no problem. However, lots of tiny screws and minute particles of paint also end up in space. They fly at orbit speed, many kilometers a second. So even tiny particles of paint, only a millimeter in size, for instance, could go right through my arm. This makes them highly dangerous. But when they re-enter the atmosphere, paint particles, screws, they all burn up. Apart from huge things like the glass lens of a telescope. Unchecked and still intact, it would crash into the Earth's surface. So as we see, it depends a bit on the composition of things and after what period of time they come down, whether they burn up or really leave holes in the Earth.
Those sonic booms announcing.
The extent of the problem revealed itself after the first few flights of the space shuttle. NASA found countless traces of collisions with debris, especially after flights to the Hubble Space Telescope at an orbital height of some 600 kilometers.
Landing system that allows the commander and pilot to guide the vehicle as it makes its final.
When the space shuttle landed, the windows and lots of other areas revealed a large number of impacts. The same with the solar cells brought back from the Hubble Space Telescope. Assessment at the ESA laboratory documented several thousand pits, some of micrometer, others of millimeter size, some clearly visible to the naked eye. A fantastic database for researchers, but it is, of course, also evidence of the major threat lurking at this orbit height.
Meanwhile, the problem has also inspired Hollywood.
Look, we need to get the hell out of here. Need some help there, man? No, don't wait for us.
He's stuck!
Man down!
Houston, the
Man down!
Copy. Houston, copy.
So exactly how accurate is this scenario of space junk hitting the shuttle and the space station as we saw in the film Gravity? What happened is that a particle of scrap impacted on a satellite and shattered it too, thus creating thousands of new parts. Naturally, these pieces of debris also have an orbital speed of 7 to 8 kilometers per second, and they fly apart. After about a day, they form a cloud between 300 and 400 kilometers wide. At the same time, the fragments disperse along the orbit, along this ring. In other words, it's relatively unlikely that I'll be hit by lots of scrap particles, if at all, in fact, by just one. And besides, what is 8 kilometers per second? Well, if a particle was behind me only a second ago, I couldn't even see it because it was so small. 1 second later, it has already hit me. In other words, you see nothing of the scrap particle, in contrast to what we saw in the film.
But space junk doesn't only pose a threat to astronauts. Today, more than 1,000 active satellites are orbiting our planet: communication, weather, and Earth observation satellites. GPS tracking alone accounts for more than 30 satellites. Every modern cell phone processes data from space. Consequently, every malfunction or loss of a satellite affects us on Earth.
By and large, we are simply unaware of how dependent we are on spaceflight. We all have a navigation system in our car without perhaps realizing that the signals for it come from space. Nearly everyone today receives TV programs via satellite. Weather forecasts are the most normal thing in the world, and also climate research is based on satellite technology. We're totally dependent on services from space. If we take the same approach to spaceflight as we have done up to now, without any avoidance strategies, in a few years' time, we might no longer be able to use some orbits for spaceflight.
In February 2009, the Russian satellite Cosmos collided with the communication satellite Iridium, an absolute disaster.
The two collided with an impact velocity of 40,000 kilometers per hour. It was a lateral collision that resulted in 3,000 particles of scrap. We can reconstruct what happened. A collision at that speed would send a shock wave through the satellite's entire structure, more or less completely demolishing it.
With fragmentation of that kind, the scrap particles first spread along the orbit. A cloud of debris forms, and this cloud is pulled apart by orbital mechanics. The scrap spreads out along the orbit. This happens within 1 or 2 days. Then, effects resulting from the oblateness of the Earth also cause the planes of the orbits to turn varyingly. After months or years, depending somewhat on the angle to the equator, the entire explosion cloud has spread evenly around the Earth within a fairly limited height shell.
The thousands of scrap particles now threaten other satellites. Each of these parts can trigger a new disaster.
So when a scrap particle destroys a satellite, generating thousands of new particles, each of which can destroy another satellite, we're talking about a snowball effect. Millions of new particles are formed. Scientists call this snowball effect the Kessler effect. The point is, the Kessler effect begins when a threshold value is exceeded. Yet we do not know for certain whether we have already exceeded this threshold value or not. But irrespective of what we do, even if we stopped space flights altogether and never put another satellite in space, this Kessler effect would simply increase the amount of space junk exponentially, and we would not be able to do anything about it.
Satellite destruction tests have exacerbated the situation. In 2007, China used a rocket to blow up one of its own weather satellites.
Doing something like that is a major blow to spaceflight. And the Chinese are not the only ones to have carried out such tests. The Russians and the Americans also did in the 70s and 80s. However, they chose targets that were much lower in the atmosphere.
The way that was done, the choice of the orbit for the collision was not good. Actually, it could not have been worse. Because that orbit is really crowded with operational satellites and the results of preceding release events. Carrying out an experiment there was not a wise decision. Shooting down the Fengyun, their own weather satellite, was an out-and-out demonstration of power by the Chinese. It was designed to show the Americans that China could destroy U.S. satellites. The aerospace community was horrified. Why? Because 40,000 new pieces of debris were created in a single action. They will remain in space for around 1,000 years, and over that long period could destroy many other satellites. Why will the debris remain up there for so long? Well, the weather satellite was orbiting at a height of 850 kilometers. On this scale, that's about this distance. At that altitude, the atmosphere is so thin that air resistance will only gradually slow down the particles. So it will take about 1,000 years for them to burn up. Around 9 months later, by the way, the Americans hit back. They destroyed their own military satellite at a height, however, of 200 kilometers. At that altitude, the atmosphere is so dense that the parts rained down and burned up within 2 or 3 months. So that was a counter-demonstration. We can do that too.
When pieces of debris enter the atmosphere, they burn up. Everything's fine. But some pieces of scrap also hit the Earth's surface.
For something to survive re-entry into the Earth's atmosphere depends a little on the mass and consistency of the object. As a rule of thumb, you could say that any object weighing more than a ton will certainly have fragments that could hit the ground on Earth.
This includes the upper stages of rockets and particularly heavy satellites.
We have objects re-entering every day. Of the 18,000 objects in space that we know of, several hundred a year will re-enter. Once a week, however, in other words, 50 times a year, something comes back to Earth that has a mass of more than 1 ton. That could mean such an object surviving re-entry, especially if heat-resistant material is on board, like titanium or stainless steel, which is often used for the fuel tanks. Indeed, such fuel tanks are frequently found on the ground. So far, however, no one has ever been injured by this material. The chances of this happening are still remote.
The objects that do not return orbit our planet for years or even decades. It is not only civilian aerospace that monitors these parts. A special unit of the US Armed Forces also focuses on them.
We have 700,000 objects that are bigger than a bullet. Only 18,000 of them are detectable, and they, in turn, are at least the size of a football. Otherwise, we would not be able to see them from Earth. The Americans have a system which was originally conceived for ballistic missiles, and it still serves that purpose. The positive side effect of this system is that it enables very good information to be obtained on basically everything moving in orbit. This is done systematically. The data are shared, and we use them to take evasive maneuvers. In other words, we can avoid these 18,000 objects, and we do.
The Satellite Control Center of ESA, the European Space Agency, is located in Darmstadt, near Frankfurt. Here, evasive maneuvers are planned and executed. But the best way of minimizing the danger is not to leave any space debris behind in the first place.
Avoiding explosions is particularly helpful, and in recent years we have actually been very effective in this. The operators of satellite launch systems also examine their rockets with regard to their tendency to explode at the end of a mission. Avoidance measures include ensuring that residual fuel is completely burned, opening the valves to release fuel into space, and shutting down all latent energies on board. This applies to launch systems like rockets and also to satellites at the end of their mission.
In future, it is hoped all newly launched satellites will meet these criteria.
Actually, building a satellite so that it will generate less debris and scrap is a lot cheaper than bringing it back later with a robot mission.
Nevertheless, the next few years will see a marked increase in the number of collisions in space.
Who pays for collision damage? First of all, it must be said that every satellite operator can choose whatever orbit they want. There are no restrictions. What's more, a satellite cannot change its orbit. That's normally the case. What it means is that if we have several satellites, now and again two satellites can encounter and even hit each other. As a rule, this doesn't happen. On average, satellites are several thousand kilometers apart, so a collision is extremely unlikely. And since no one can actually prevent a collision, each operator has to carry the cost of any damage himself. Besides, just imagine there's a tiny screw flying through space. This screw then destroys a satellite. But how do we know where the screw came from? It's a different case if a satellite crashes and causes damage on Earth. The international ruling then is that the manufacturer, or to be more precise, the country of the manufacturer, has to pay. Period.
To get a grip on the problem, scientists are working on new strategies. One is for dead satellites to be recovered.
These objects are traveling at extremely high speed, so any recovery vehicle would have to be moving at the same speed and also be able to snare an object.
Quite a few ideas have been put forward for capturing satellites or large pieces of debris. They include grabbing a dead satellite with robotic arms, or catching space scrap with a net and dragging it back towards Earth. There is no limit to scientists' imagination.
The object could be attached to an engine module. The engine module would then be fired and the module with the upper stage brought down. In lower orbits, a large balloon could also be secured to the upper stage and inflated. The large cross-section would offer air resistance and thus reduce the life of the upper stage in orbit and also bring down the object.
Other ESA studies envisage a sail being attached to a disused satellite. Residual air resistance would increase, forcing the satellite out of its orbit. Or the satellite could be bombarded with particles and thus pushed to a lower orbit from which the Earth's gravitation would pull it back down.
All these principles, however, are technically demanding and call for a legal statement. I can, of course, retrieve my own objects, but I do not have the right to remove those belonging to other nations.
The biggest human-made structure ever removed from space was the Russian space station Mir. Launched in 1986, in 2001 Mir reached the end of its service life. After abandoning the station, the Russians did not want to leave the 124-ton giant pile of scrap in orbit.
I'm often asked why a space station cannot be operated on a permanent basis. Well, like a car, a space station has a limited service life. A car has a life of around 15 years, a space station one of 15 to 20 years. Mir was designed for a lifespan of 7 years, but it lasted for 15. And believe me, at the end of its service life, something like that stinks to high heaven. It becomes moldy inside, and for that reason alone, it cannot be continued. But how do you bring something like that back down? You can't just let it crash. And every space station will crash simply because the residual air resistance will slowly bring it down. But if a space station plummeted unchecked, it could crash into a city and kill millions of people. Disastrous. So it has to be brought down under control. And that always takes place in the middle of the Pacific Ocean, which covers half the Earth's surface. And that's exactly what was done with the Mir station.
Mir was one of the Soviet space program's greatest successes. Before the International Space Station was launched, it was humankind's only permanently occupied outpost in space. Over a period of 10 years, it was assembled in space from several modules and continuously enlarged. After the end of the Soviet Union, this unique research vessel was also used by Western space agencies.
It was like a home to us, a place where we experienced some incredible things. Being in space for the first time, working up there, performing all these fantastic tasks, engaging in superb cooperation with my 2 Russian colleagues. Those are the thoughts that come flooding back. And then you think, what a shame, it's now going to burn up in the Earth's atmosphere.
Russia operated the station way beyond its envisaged service life, but joint plans for a new space station, the ISS, spelled the end for Mir. The Russians could not have continued to operate it on their own.
When Mir was brought down in 2001, in the background, the International Space Station was already starting to grow, and there was just not enough money available for both of them. So Mir was actively taken out of the heavens, even though it was fully functional. Our Russian colleagues were very sad to see that happen.
Left in orbit, within a few years, the station would have plunged to Earth uncontrolled. Because of its size, numerous pieces of debris would have survived re-entry. Russians, Americans, and Europeans worked together to bring it down safely.
If the space station had crashed down unchecked, it would have constituted a huge danger. But at that point in time, the Russians were very open. All information important for assessing the risk was made internationally available. They supplied data like orbit tracking data from European radar. The Americans did something similar because the more closely an orbit is observed, the better it can be determined, and the area where the satellite will come down can be forecast more precisely.
The complicated maneuver got underway on March 23, 2001. With a calculated shunt from Progress, a spacecraft that had docked onto Mir, the station was first pushed into a lower orbit.
The Russians brought down Mir with 3 shunt maneuvers. The first maneuver took place 4 orbits prior to re-entry. The second, 3 orbits before re-entry. There was then a 1-orbit pause for assessment. Then, in the final orbit, the Progress, which was docked on, gave a major thrust, or de-orbit burn. It was carrying a large amount of fuel, especially for this purpose. The major maneuver resulted in re-entry, and the re-entry zone was in a safe area.
Die Wiedereintrittszone war dann in einem sicheren Gebiet.
Mir entered Earth's atmosphere over the Pacific. The station broke up. The various parts burnt up in the atmosphere. Spread over an area of 1,500 kilometers, debris from Mir fell into the ocean far away from any civilization. The operation was a success. But it is not only debris that poses a threat in space. Outside the Earth's atmosphere, many dangers await us.
No trip into space is good for the health, so there's possibly a few percent greater likelihood of developing cancer. So far, there have been so few astronauts that we don't have the appropriate statistics as to what really happens to the body. Long-term stays on Mir or on the International Space Station result in increased exposure to radiation, but everyone is aware of this.
Long-duration stays are designed to determine how great this exposure is. American astronaut Scott Kelly spent a total of 520 days in space, longer than any other NASA astronaut.
I think mostly it'll be more of a challenge in that I am getting ready to be gone for about, it'll be really about 14 months, which is a pretty long time for me, leaving from home and leaving a 19-year-old at home in my house. So that's going to be a little bit more challenging this time.
Kelly is a former US Navy fighter pilot, just like his identical twin brother Mark, who is 6 minutes older. Like his brother, Scott Kelly was selected to be an astronaut by NASA in 1996. The long-term mission to the ISS got underway in March 2015. A Soyuz rocket took Kelly up to the ISS from Russia's Baikonur spaceport. He is more than familiar with the space station. He already spent 6 months on it as part of an earlier mission. But this time he spent 381 days in space. His mission was not without risks. Kelly was permanently exposed to cosmic radiation for an entire year, comparable with a situation on a flight to Mars. And that's precisely what NASA wants to explore.
Someday we're going to go to Mars, and we have the facilities on board the space station to really study the effects of space on longer duration space flights.
Scott Kelly lived and carried out research on the space station for over a year. But the most important experiment was Scott himself and his twin brother Mark, who remained on Earth. What effect does cosmic radiation have on humans? How does a body change after a year in weightlessness? How does a human being cope with the mental strain of such a long spaceflight? These are questions NASA needs answers to. During his stay on the ISS, Kelly was at least able to see the Earth. On their journey to Mars, future explorers would not see much more than the black nothingness of space. The twins' study with the two astronauts, Scott and Mark Kelly, helps in the preparation of interplanetary journeys.
Where humans are concerned, there are two different kinds of dangerous radiation in space. First, we have GCR, galactic cosmic rays, individual iron atoms, which are created somewhere in the universe by supernova explosions, and then bombard me at almost the speed of light. What do they do to my body? They penetrate deep into it, generating what we call secondary radiation, a whole swarm of protons and neutrons which shatter my genes, my DNA. This usually causes cancer. As a result, my life expectancy is reduced. How great is this effect? Well, about 100 times greater than what I experience on Earth. And then there's another important type of radiation, solar flares, proton rays that are hurled into the universe through solar eruptions. In other words, if the sun is at the back there, the entire load of protons hits me. They impact at a speed of 400, 500, or 600 kilometers a second and also cause cancer. Here, too, the radiation I'm exposed to is about 100 times greater than on Earth.
In this respect, spacewalks are particularly dangerous. Spacesuits offer no protection from cosmic radiation, so astronauts are only allowed to spend a limited time spacewalking. The first man to step into space was Alexei Leonov. In 1965, he climbed out of his spacecraft and hovered above the Earth. He was connected to the spacecraft solely by his spacesuit's umbilical cord. The first American to venture out into the endless void was Edward White. He too was protected solely by the thin material of his spacesuit. Without a spacesuit, a human would die in next to no time. He wouldn't burst, as is often shown in films, but the lack of pressure would cause his blood to boil. Basically, though, an unprotected person in space would suffocate from lack of oxygen. Spacesuits are constantly undergoing further development. A suit consists of several layers of special fabric. Aramid fibers are used, and there is also a layer of aluminium. The spacesuit has to protect the wearer from the hostile environment of space. It regulates temperature, warming the astronaut in the extreme cold of space and cooling him when he is exposed to the sun. It provides an oxygen supply, removes exhaled carbon dioxide, and maintains an even pressure. And it ensures communication with the outside world. Catering for all eventualities, astronauts also wear highly absorbent underwear, a kind of adult nappy. In a spacesuit, an astronaut is independent of onboard system for several hours. To a certain extent, he is in his own mini spacecraft. A spacesuit not only has to be absolutely leak-proof and resistant, it must also allow the astronaut to move freely and work unimpeded. The only thing it cannot offer protection against is so-called hard radiation.
Classic spacesuits can't offer protection against radiation because then they'd have to be made of lead, so you wouldn't be able to move in one. A spacewalk lasts for maybe 5 or 6 hours, so the risk from radiation really is low. Pilots flying over the Atlantic all year round are probably exposed to more radiation. You must always remember that it is the dose that matters. The dose depends on how powerful the radiation is and the length of exposure to it. If that time is kept short, then everything is fine.
The most dangerous radiation comes from the sun. Solar eruptions hurl out masses of energy-rich particles. This hard radiation not only disturbs radio communication, it also threatens the lives of space travelers. These eruptions can easily be observed from Earth. Astronomers study our life-giving star with solar telescopes, the most modern of which is located on Tenerife. Gregor, as it's known, is operated by the Kiepenheuer Institute for Solar Physics. On Earth, we are protected by our planet's magnetic field, but in space, a human being is unprotected from hard radiation.
Particles are also released. If a solar eruption had occurred during the moon landings, for example, the exposure to radiation would have been much higher. So the astronauts can count themselves lucky. But that, and all the many other risks involved, were all accepted. And indeed, when you look at all those risks, you have to say that the moon landings could have gone much differently.
Solar eruptions cannot be predicted. Sometimes there is little activity. But on other occasions, huge explosions occur with vast quantities of material being hurled into space.
How do these solar flares originate? What damage do they cause on Earth or in space? Can we be warned in advance? Solar flares are caused by solar eruptions. In other words, an eruption on the sun's surface sets off an entire wind, a flood of elementary particles, protons with a velocity of 800 kilometers per second. And at that speed, they head towards the Earth. Fortunately, we get an advance warning because the eruption can be seen with a telescope. Entire satellite systems exist for this. Like SOHO, a satellite that focuses solely on the sun. When a solar eruption is observed, the light from it takes just 8 minutes to reach us. But the wind, the effect, takes 2 days. So normally we have 2 days advance warning. It means that we have to align our satellites in space to prevent their solar cells from sustaining a direct hit. If their position is altered, they will not be hit head-on. The space station is also realigned. When the solar wind arrives, it passes over the magnetic field line to the northern latitudes, characteristically affecting Canada, Norway, or Sweden. So we do have an advance warning period, and that's good because it means that any damage is actually relatively minor.
But even so, spaceflight remains a dangerous enterprise. There is still no really effective protection from solar eruptions and cosmic radiation. Any astronaut on a spacewalk is aware of these dangers. That is the nature of our universe. We can only try to minimize the risk. But space pollution is homemade, and it is only a question of time before space debris hits more satellites. The volume of dangerous debris in space is increasing. All we can do is locate and observe it and hope that no further disasters occur. Humankind has made itself dependent on satellites in space. They make our lives easier and help us to understand processes and changes on our planet. But this technological infrastructure is in danger. Every additional piece of debris in orbit around the Earth threatens these advances.
Space pollution is a global issue. There are no nation-specific areas in space. Every collision results in global pollution. So in the final analysis, we are all involved, and we should all participate in the cleanup. Here, the polluter pays principle is very difficult to apply. So basically, every nation involved in spaceflight must participate and implement measures. First of all, avoidance measures. Every satellite operator or anyone wanting to launch something could, for instance, be asked to make a deposit. He would then get it back at a later date, following proper retrieval of his object.
But international agreement on these matters still needs to be reached.
Space junk is dangerous, without question. I think that has become clear. Even minute particles no bigger than my fingertip can destroy entire satellites. They're then dead. And there are millions of these particles flying around up there. For the time being, the danger is not all that great. A satellite is wrecked once every 15 years or so. But the risks are growing because more and more junk is being created simply through the Kessler effect. So what can be done? Not only must we avoid creating more debris, we also need to remove the old particles that are contributing to the Kessler effect, not just for our own benefit, but also for the benefit of those who want to continue operating satellites and traveling into space. That costs money, and no one is willing to pay.
For a long time now, Earth's orbit has become part of the infrastructure of our modern world. Yet space remains dangerous for humans and our technology. That's in the nature of things, but human endeavors pose the greatest threat.